Hello everybody. In this video, we're going to learn about row-reduced echelon form, or RREF for short. Now, our ultimate goal is to solve linear equations. And in the previous video, you learned how to convert linear equations to multiple different forms. You could either have a system of individual equations, a vector equation, a matrix equation, or an augmented matrix. In this video, we're going to learn a technique to solve using the augmented matrix form. And this is our strategy. We're going to convert an equation from any of those forms to an augmented matrix. And then we will reduce the matrix values to ones and zeros using row operations until the ones form an echelon, which is a word meaning stair-like or kind of diagonal, an echelon pattern or form. And that's why this is called reduced row echelon form. It's what the matrix will look like when we're all done. So most of this video will be about how to calculate it, but first we need to define it. But before we even define it, let's see some examples and why, once an equation is in row reduced echelon form, it's so easy to figure out the solution. So here is an example of an augmented matrix which is in echelon form. Notice the ones kind of form this little staircase-like pattern. And if you were to convert this augmented matrix back to a system of equations, so you have 1x plus 0y plus 7, but that simplifies to just x equals 7. Similarly, the second row corresponds to 0x plus 1y equals 2/3, but simplifying that, you get just y equals 2/3. And so if something's in this form, the solution is basically the numbers in the right-hand column. Let's say we have a larger matrix. Again, notice the pattern of ones and all these nice zeros here. When we convert this augmented matrix, we'll get this system of equations. But all the zeros, of course, drop out, and we're left with the terms with the ones. And then we can read off the solution: x equals 5, y equals 2, and z equals 4. And so a matrix in this form will have exactly one solution. Now, there's other possibilities as well. For example, in some equations, you'll have infinitely many solutions. Denote that with the infinity symbol. So here's another augmented matrix, and this is also in reduced echelon form. And so the ones form this staircase-like pattern. Right? There's kind of no space left to put another one in this last column. But if you were to convert this to a system of equations, you'd get 1x plus 0y plus 5z equals 3. And the second row would be 0x plus 1y minus 2z equals 6. Now, if you rewrite these, it's easy to solve for x and y. You could move the terms involving z to the other side. So you have x in terms of z and y in terms of z. There is no third equation which tells you what z should equal. So in a situation like this, z is called a free variable. There's no restriction on z. Z could have any value, and for every value you pick for z, you get a different solution to your equations. So for example, if you choose z equals 0, you could plug that into these equations up here, plugging in 0 for z. You'll be left with x equals 3 and y equals 6. Which means your point, your solution to the equations, is 3, 6, 0. Now, similarly, you could let z equal 1, plug that into your equations to find x and y, and you'll find that you have the point x, y, z equals negative 2, 8, 1. Or you could plug in z equals 2 and get another point, etc. You could, again, infinitely many choices for z will give you infinitely many solutions to the corresponding equations. Now, it's not always the last variable, which would be free. So here's another example of a matrix which is in echelon form. In this case, again, the ones, along with the zeros, they kind of make a nice staircase-like pattern. And if you were to rewrite this expression, this augmented matrix, as a system of equations, you would get x equals 10 minus 3y, just solving for x right away, and z equals 8. The last row's kind of strange. Almost everything drops out, and you're left with 0 equals 0, which is always true and not useful. It doesn't give you any new information. No matter what you pick for x, y, and z, you don't have to worry about this equation. In this case, we can solve for x and we can solve for z, right? The variables and the positions corresponding to the ones, but we can't solve for y. So here, y is a free variable. Every value you choose for y will give you new values for x and z, leading you to your solutions. So once again, you could pick y equals 0 and plug that in here. You would get x equals 10, y we chose to be 0, and z is always 8. You could choose y equals 1 and get another point, y equals 2 and get another point, and so on. So we have infinitely many solutions sometimes. That happens when we're solving equations. And there's a third possibility here. There might be no solutions, right? Let's take a look at this augmented matrix. Again, the ones make this staircase pattern, but notice there's a 1 in the rightmost column this time. If you were to translate this augmented matrix back into a system of equations, the first row is 1x plus 4y equals 0. The second row is 0x plus 0y equals 1, which should make you a little bit nervous. This is saying 1 equals 0, 0 equals 1. That's not true. The second equation is always false. So no matter what values you pick for x and y, you cannot satisfy all of these equations. There is no solution to this set of equations represented by this augmented matrix. So for something like this, you'll have no solutions. Now, what about this slightly larger augmented matrix? Once again, this is an echelon form. And if you write out the equations corresponding to each one of these, right, the first row corresponds to x plus 2y plus 1/3 z equals 0. The next row corresponds to, after you simplify, 0 equals 1. And the last row corresponds to 0 equals 0. Now previously we said, when 0 equals 0, that gives you no new information. Also, you have a couple of free variables here, right? In fact, we had that for the last case too. In this case, y and z are both free. And in theory, you could pick anything you want for y and z. That tells you a value of x. But this second equation is never true. It doesn't matter if 2 out of the 3 equations are true. All the equations must be true for x, y, z to be a solution. So whenever you have an equation like this, 0 equals 1, or 0 equals any constant, that's not 0, there will be no solutions to your system. It doesn't matter if there's free variables, it doesn't matter if there's equations that are always true. This equation kind of ruins it for the entire system. No solutions. Now, what do all these matrices have in common? I've said they're all examples of reduced row echelon form, but let's make that concept a little bit more precise. Right? In each one of these matrices, on the left we have the ones corresponding to one solution. In the middle we have the ones corresponding to infinitely many solutions. On the right side we have the matrices corresponding to no solutions. But across all of these examples, in every row, the first non-zero number is always 1. Right? Sometimes there's a row of all zeros, but the first non-zero number is always 1. So that's one distinguishing feature. Additionally, above and below each of these ones, the ones that are the first numbers in each position, it's always zeros above and below the ones. Right? Zeros make the equations a lot simpler. That's why it's called reduced echelon form. We're trying to make these numbers as simple as possible. Can't get much simpler than zeros and ones. So that's our next condition, that above and below every zero, there are above and below every one, there are zeros. There might still be numbers which are not zero, right, this 3, but that's okay, because that's not one of the leading ones in a row. Finally, these ones occur in a staircase-like pattern, right? So they kind of go across and down. Sometimes you might go across multiple columns before you go down a row. You might go across multiple columns before you go down a row, but you have that echelon or stair-like pattern. And these conditions define reduced row echelon form. If I could have named this, I would have called this the ones and zeros staircase pattern, but some mathematician decided to call it this, so everyone refers to it as reduced row echelon form. Now, hopefully I've convinced you by now, reduced row echelon form is a wonderful thing. It allows you to basically read off the solutions. The next task, in fact, this is what we'll do for the rest of this video, is learn how to use row operations to convert any augmented matrix to row reduced echelon form. And these are the basic steps, and we'll do lots of examples. The first step is going to be to multiply or divide a row by the first non-zero number in that row to convert it to a 1. One of the row operations is you can multiply or divide a row by a constant number. So for example, if I had this augmented matrix down here, I would take this first row and divide everything by A. That would put a 1 in this first position. Then, once you have a 1 to work with, then you can add or subtract multiples of this row, the row containing the 1, from the other rows to create your zeros, both above it and below it. So again, in this augmented matrix here, after dividing that first row by A, then I could subtract a multiple of this first row to create a 0 in the position where C is. You can also rearrange the rows if you want at any time to make sure you get that nice staircase pattern. And then you just repeat these steps, and it'll get simpler every time until you're in row reduced echelon form, at which case you can just read off the answer. All right, those are the steps. Let's see some examples. And at each step, I'm also circling the number that I'm focusing on, the number that I'm going to simplify. And in this example, we'll also see some notation I use to kind of make it clear what steps we're taking. Let's say you start with this system of equations. 2x plus 4y equals 8, and 7x plus 6y equals 5. First, let's write down these values in an augmented matrix. Right, so the variables are lined up, the constants are on the right. The augmented matrix for this system would be 2, 4, 8, 7, 6, 5. First, I'm going to focus on this 2, and I'll divide that first row by 2, or equivalently, I'll multiply that first row by a half. Now this notation here, times 1/2 next to this row, indicates that in the next matrix, all of these values will be multiplied by 1/2. The second row, there's nothing written next to the second row, so that row will stay the same. We'll take it one row at a time. So the row 2, 4, 8, 2 times 1/2 is 1, 4 times 1/2 is 2, 8 times 1/2 is 4. So that first row becomes 1, 2, 4. All right, every time we create a 1, we're going to add and subtract multiples of this row containing the 1 from the other rows to zero out the numbers that appear above and below it. So in this case, I'm going to focus on this 7. In order to get rid of this 7, I want to subtract from this row 7 times the first row, 7 times row 1. And so this notation here indicates that from this row, I'm going to subtract 7 times row 1. And so this row is changing. I'm not actually going to change the first row, I'm just using row 1 in this calculation. So first, I'll do 7 minus 7 times 1. That's a 0. 6 minus 7 times 2, right? So row 1 means, the number directly above it. So 6 minus 7 times 2, that's 6 minus 14, that's negative 8. And then 5 minus 7 times 4, that's 5 minus 28, that's negative 23. Right, so after doing that subtraction, this is our new augmented matrix. Next, I'm going to focus on this number here. Right, I've done everything I can do in this first column. I cannot make it any simpler. So in the second column, here I can turn this negative 8 into a 1 by multiplying this row by negative 1/8. And it's also worth pointing out that when I multiply by a number, I'm not destroying my earlier progress, right? Because multiplying 0 by something doesn't change the value. So multiply the numbers in the second row times negative 1/8. We're not changing the first row at all. And then the second row becomes 0, 1, 23 over 8. Okay, it's a fraction. Next, we're going to turn our attention to this 2 up here. Right, so I want to use this 1 we just created to zero out any numbers above and below it. So we're going to subtract a multiple of this row from this row. Right, and so we can do this number, which is 2, minus 2 times the numbers in row 2. Now another thing to take note of is that these steps are being followed in this order so we don't ruin any progress from what we did before. This 1 that we created initially, that's not going to change because we'll be subtracting 2 times 0. Right, so this 1 stays as it is. All right, so from row 1, let's subtract 2 times the numbers in row 2. So 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. And 4 minus 2 times 23 over 8. I'm going to do a little bit of math in common denominators, but that turns out to be negative 7/4. And then at this point, we have row-reduced echelon form. Right? We've got a staircase pattern of 1s. The first number in each row is a 1, and above and below each one is a 0. So we're done. And we can just read off the solution now. If you want, you could write out 1 times x plus 0 times y equals negative 7/4. And then when you simplify, it turns into x equals negative 7/4. Similarly, y equals 23 over 8, and that's your solution. It's always good to check your answers if you can, and checking your answers just means plugging them into the original system of equations, make sure that works out. So if you plug in negative 7/4 for these x's, and plug in 23/8 for the y's, and then do some math, you will get the values you expect at the end, 8 and 5. Now, the key here is to keep on practicing. You learn math by doing math. We're going to do even more examples. It seems like it takes a while at first, but that's because I want to take my time and explain every step. The more you do this, the easier it will go. So let's do another example. In this case, let's do 2 equations with 3 variables. So 2x plus 3y plus 4z equals 2. 3x plus 4y plus 2z equals 3. Since all the variables are lined up, the constants are on the right-hand side, we can read off these coefficients and create the augmented matrix 2, 3, 4, 2, 3, 4, 2, 3. All right, we'll begin. Again, I'm going to pay attention at each step to the number outlined in green or circled in green. So first, let's turn this 2 into a 1. We'll do that by multiplying the first row times 1/2. 2 times 1/2 is 1. 3 times 1/2 is 3/2. 4 times 1/2 is 2. 2 times 1/2 is 1. All right, next, use this 1 to zero out the number below it. So we can subtract a multiple of this first row from the second row. So what we'll do is the second row minus 3 times the numbers in row 1. So 3 minus 3 times 1 is 0. 4 minus 3 times 3/2 is negative 1/2. 2 minus 3 times 2 is negative 4. And 3 minus 3 times 1 is 0. And so this is definitely getting simpler. Next, looking at the second row, since we're done with that first column, looking at the second row, I want to turn this circled number into a 1. So I can take negative 1/2 and multiply by negative 2. I need to multiply this entire row by negative 2. 0 times negative 2 is 0. Negative 1/2 times negative 2 is 1. Negative 4 times negative 2 is positive 8. And 0 times negative 2 is 0. And finally, I'm going to remove this number. I'm going to change it into a 0 by subtracting a multiple of this row, right above the 1. So I can do subtract 3/2 times the numbers in row 2. All right, so 1 minus 3/2 times 0 is 1. 3/2 minus 3/2 times 1, that's 0. 2 minus 3/2 times 8, that's negative 10. And 1 minus 3/2 times 0, still 1. And then at this point, once again, we have reduced row echelon form. Right? We've got our 1s at the beginning of each row, 0s above and below the 1s. If we write this as a system of equations, we have x minus 10z equals 1 and y plus 8z equals 0. So in this case, we can write x and y in terms of z, and z has no equation which forces it to have any value. So z is a free variable, x is 1 plus 10z, and y is negative 8z. Right? So that's the solution to this equation. You can just say z equals free. To check these values, you just pick a value for the free variable. So for example, you could let z equal 1. And then you get a point, which is a solution. In this case, if z equals 1, plugging that in here and here, you get x equals 11 and y equals negative 8. Z we chose to be 1. And then plug that point into your original equations and make sure they equal what you expect them to be. Right, so we know that this equation is correct. Now I put a little asterisk up here because the procedure I mentioned earlier, it will always work, but sometimes you might see a step which could be a little bit quicker or a little bit easier. For example, here, I have a negative 1/2 and a 3/2. You can deviate from the suggested procedure if you think it'll make things easier. So here, alternatively, instead of multiplying this by negative 2, we could immediately zero out this term by subtracting 3, or no, by adding, I guess, 3 times row 2 to row 1. Right, so we could zero out this term first, and then multiply this row by negative 2 later. No matter which way you go, though, you'll end up with the same solution. So feel free to use a different approach or a different order if it works out easier for your specific example. Now, one thing I'd like to mention about this previous example, it relates to the kinds of problems we were doing before we started studying matrix algebra. In this example, we had equations of two planes. And the solution we had, here's x, y, and z, and we have infinitely many solutions. As we know from before, the intersection of two planes is very frequently a line. To find the equation of the line, we could rewrite this solution in a different form. Instead of just saying z equals free, we could rewrite z using the variable t, like the parameter. So z equals 1t plus 0, and then write everything else in terms of t. And in this case, it looks like the equation of a line. So we could gather terms, right? Every point x, y, and z is equal to the coefficients of t, form your slope vector, 10, negative 8, 1 times t. Then these constants form a base point, 1, 0, 0. So this is another way to find the line of intersection between two planes. Now, here's another example. Let's say, once again, we have two planes, 3x plus y minus 2z equals 4, and 6x plus 2y minus 4z equals 5. Everything's lined up, constants on the right. If you write the augmented matrix, we have 3, 1, negative 2, 4 for that first row, and 6, 2, negative 4, 5. And in this case, to avoid fractions a little bit, instead of multiplying this first row by a third, you might see that it could be a little bit simpler to immediately subtract 2 times row 1 values from row 2. Right, so let's go ahead and subtract minus 2 times row 1. 6 minus 2 times 3 is 0. 2 minus 2 times 1 is 0. Negative 4 minus 2 times negative 2, that's minus 4 plus 4, so that's 0. And 5 minus 2 times 4, that's negative 3. Right? Whenever you see an equation like this, all zeros on the left-hand side and a non-zero number on the right, you can actually stop here. You don't really need to go all the way to row-reduced echelon form once you've deduced that there's no solution. Right? In this case, if you rewrote this row as an equation, you'd get 0x plus 0y plus 0z equals negative 3, which is telling you 0 equals negative 3, which is not true. So no matter what you pick for x, y, and z, you'll never make the second equation true. In other words, there's no solution to this system of equations. Now, once again, geometrically speaking, visually speaking, these two equations are planes, flat surfaces in three-dimensional space. If there's no solution, what that's telling you is that the planes are parallel. Now imagine these as two sheets of graph paper, and one is just lying, like right above the other. Right? They're not inclined, they're not going to intersect at all. Another way to see these are parallel, if you had just started with the second equation and multiplied it by 1/2 right away, you might notice that you get the same coefficients of x, y, and z. So these two planes have the exact same normal vector, the same perpendicular vector to both. And that also tells you that they're going to be parallel, since these are different numbers on the right-hand side, but the same normal vector. It's another way to determine they don't intersect. All right, let's do one more equation. In this case, we have 3 equations and 3 variables, so we have a much larger augmented matrix. And this is really the largest system of equations we're going to do in this course. But this method, row-reduced echelon form, it applies to any number of equations. It's one of the fastest ways to guarantee finding a solution. Now, as we write this in an augmented matrix, thankfully, there's a bunch of ones and zeros in it already. Right, so we have a 1 in this top left position. We have a 0 down here as well. So I'm going to turn my attention to this circled number here. I'd like to zero that out. So in this case, we can subtract the numbers in row 1 from row 2. So we'll do row 2 minus numbers in row 1. 1 minus 1 is 0. 1 minus 2 is negative 1. 2 minus 1 is 1. And 6 minus 4 is 2. Now, once you become more comfortable with row operations, which will happen the more practice examples you do, you can do operations with multiple rows at the same time, right, if it's okay. Right? So, for instance, I've got a negative 1 here. What I'd like to do next is turn this negative 1 into a positive 1. Also, I'd like to use this value in the middle, so like use row 2, to zero out the numbers above and below it. Right, so just to save some space, which is not necessary, but you can if you wish, we'll just do all 3 steps at once. So from row 1, we can add 2 times the numbers in row 2. So 1 plus 2 times 0 is 1. 2 plus 2 times negative 1 is 0. 1 plus 2 times 1 is 3. And 4 plus 2 times 2 is 8. Gives us a 0 there. The second row, we'll multiply those by negative 1. 0 times negative 1 is 0. Negative 1 times negative 1 is 1. 1 times negative 1 is negative 1. And 2 times negative 1 is negative 2. It's our second row. For the third row, we're going to add 3 times the numbers in the second row right here. So 0 plus 3 times 0 is 0. 3 plus 3 times negative 1 is 0. Negative 1 plus 3 times 1 is 2. And 4 plus 3 times 2, that's 10. All right, and we actually just cleaned up an entire second column here. Next, let's turn this 2 into a 1. We can do that by multiplying this row times 1/2. So we'll have 0 times 1/2 is 0. 0 times 1/2 is 0. 2 times 1/2 is 1. And 10 times 1/2 is 5. All right, now that we have a 1 here, I want to zero out the numbers above it. And we'll do that by adding or subtracting multiples of this row. For the first row, I'd like to subtract 3 times the numbers in the third row. For the second row, to get a 0 here, I just need to add the numbers in the third row to the second row. And all these zeros make our lives a little bit easier, because these zeros aren't going to change the numbers above it. So, let's see. Here, I'm still going to have a 1 and a 0. Then 3 minus 3 times 1 is 0. And 8 minus 3 times 5 is 8 minus 15, which is negative 7. And for this row, let's see, we'll have negative 1 plus 1 is 0. And negative 2 plus 5 is 3. At this point, we're in reduced row echelon form. We can read off the solution. X is negative 7, Y is 3, and Z is 5. And once again, we can take a look and check that this equation is correct, this solution is correct, by plugging these values into all of these equations, and they should make all the equations true. And it only takes a minute to check. It's definitely worth your time. Now, geometrically speaking, this is kind of interesting. This is unlike what we've done so far. Right? We've done the intersection of 2 planes, and that gives you a line. Here, this is saying the intersection of 3 planes. 3 planes usually intersect at 1 point. Not always. It is possible to have 3 parallel planes, like layers of a sandwich. But in this case, think of it as two planes intersect in a line, and that line of intersection with the other plane just gives you a single point. Right, so three planes will typically intersect at one point, and now, thanks to augmented matrices and row-reduced echelon form, you can figure out what that point is. Now, as always, you learn math by doing math, so here's an exercise for you to try out. Here is a system of equations. What I'd like you to do is go ahead and convert this to an augmented matrix. Didn't mean to write any. Convert this to an augmented matrix of 3, 3, 7, 1, 2, 4, and use row-reduced echelon form. Right, go ahead and do row operations to simplify this and find the solution in terms of x and y. And when you're done, be sure to check your answers so you can make sure you solved it all right. And that is how you solve a system of equations using augmented matrices and row-reduced echelon forms. Thanks for watching.